The last equation I want to talk about is acceleration. Um, if you remember that acceleration is the rate in which velocity is changing, or the change of velocity divided by time. Both of those are the interchangeable definition for acceleration. So what I've done is I went ahead and I've written up the velocity equation. I'm going to take that velocity equation, I'm going to take a derivative of that velocity equation with respect to time, and I'm going to get my acceleration equation from that. Okay? So looking at that, what I want to do is I want to say the rate of change of my velocity. Okay? So that means that I have to take a derivative of everything up here. With respect to time. Now, once again, when we're taking those derivatives, we do have constants. We do have things that are not affected by time, that are constant in the system. Now, that being my maximum position and my angular frequency. Neither one of those are going to change with time. They're all going to stay the same. That's why it's a natural frequency. It wants to be there. You have to have something outside of the system forcing it to be at a different frequency than that. So those are going to be left alone. It's only this cosine function that's going to be affected. Okay, so I'm going to go ahead and bring that outside. Okay, so that's what it's going to look like when I take the derivative of that, or when I move a few terms around. Now the light is kind of blocking out that D. I'm going to go ahead and make it a little darker, see if that helps. The truth of the matter is it's not really that big of a deal. I just like to show where everything comes from. Now when I take the derivative of this, the phi is not going to be affected. The omega t is going to be affected. So what that ends up looking like when I take the derivative of that is that I've got the change in velocity over time. That equals acceleration is equal to x max times omega. Now when I take the derivative of this, this omega gets copied and brought outside. So that becomes omega squared times, now the derivative of cosine is going to be a negative sign, so I'm going to put a parenthesis around it. Negative sine omega t plus phi. Now I really don't want to leave it like that. I'd rather not have so many parentheses around. So what I'm going to do is I'm going to move that negative sign to the outside so I can get rid of that parentheses. So I'm left with the acceleration of my object is equal to negative x max. Oops, forgot my x there. Omega t, or omega squared, not omega t, times sine omega t plus phi. Okay? That is my acceleration equation. Now, once again, I'm just taking a derivative to get through these steps. Talk about a few things really quick. So, my acceleration at any given time, whatever that time may be, is equal to the negative of my maximum position times omega squared times, once again, a bound function. It goes from 1 to negative 1. The thing is, though, it's a negative bound function, which means instead of going from 1 to negative 1, it's going to go negative 1 to 1. Okay? So, x max omega squared sine omega t. Omega being natural frequency, time, t being a time, this being a phase shift once again. Cool thing, real quick, right here. That's a maximum acceleration. X max times omega squared. That turns out to be maximum acceleration. Gosh, that didn't really come out very good. I'm going to go ahead and rewrite that really quick so you can see it. Okay? Yeah, there we go. That's a maximum acceleration. This x max times omega squared. That's how fast that object's going to, that's the maximum it's going to have that change in its velocity. Okay? So that's a maximum change in that velocity is at this value right here. Okay? Really kind of cool. Just kind of falls out like that over and over again. If I were to take another derivative of it, and if anybody knows what a derivative of acceleration is, it's a jerk. It would turn out to be my maximum jerk would be x max omega cubed. If I wanted the second derivative of jerk, then it would be to the fourth, to the fifth, to the sixth, to the seventh. It just keeps going that way. That natural frequency keeps showing up that way. Okay? So this is the equation for simple harmonic motion, or the equation for the acceleration for an object in simple harmonic motion. Cool thing, another cool thing about it, acceleration is not constant in this system. You can see that it's going to change with time. It's going to oscillate up and down. It's going to hit a peak and then going to go back down. Going to hit this low point and then going to go back up. Okay? So it's not constant. When we looked at equations before, there were constant accelerations. We had to have that constant acceleration. Simple harmonic motion says no. We can deal with non-constant accelerations. We can deal with it if we know a little bit of calculus and a little bit of trig. Okay? So, third equation for simple harmonic motion, acceleration.